And hello, welcome to yet another day of physical science. Today we're going to start chapter 4, which is called Work and Energy. This chapter is kind of interesting because we're going to talk about energy from the physics standpoint, what that means, and we're going to wrap up with talking about energy from the more society standpoint. That when people say, the ideas of um, creation of energy and things like ways to make energy and renewable energy, ideas on that also. It's kind of an interesting thing because I'm perpetually need to update those notes, but yeah, that's the thing we'll be doing. Before I get into it, this is the last chapter on the first exam. Your first exam is Wednesday, March 3rd. The general idea is that these exams will be online because everything's online. That is the life we live in. That is just fact. And so here's the idea. At noon, the exams will open. Um, and what the exam will look like, well, if you want to see what the exam will look like, you know what? It'd be smart if I thought of this ahead of time. What I did is on Vanco Hall, I posted last semester's exam. And so if you go down to the exam section, underneath that there's old exams, and you can see exam 1 for 2020. And this is in the exact same way that the exam will put. There's no need to do this. It's not going to be graded, but it is a good practice exam. What it's going to be is going to have full pages of problems. Each one will have 5 problems in it. And how the exam works is you're going to do these off on paper. Just do it on your own, just write on paper. And then I want you to take a picture of each page and upload. That way I can give partial credit. And so, yeah, you just do the work on paper, take a photo, upload it. General idea is this is a 50-minute exam. I'm giving you an hour and 15 minutes to give you 15 minutes to upload. So I really, really recommend only spend 15 minutes actually doing the exam and give yourself enough time to upload everything. If it hits 105 and you don't have stuff uploaded, that's what I'm grading by. That is the deadline. So please make sure you use your time wisely. During the exam, I will be on Zoom. So if you have questions, you can log in. Do not work with other people. If you do work with other people, and I can tell, which let's be honest, most of the time people work together, I can tell. I will just fail you on the exam and do an academic warning for academic dishonesty. It is open notes because I can't control that. Yeah, 20 problems long, 5 from each chapter. So the first page will be all chapter 1. The second page will be all chapter 2. The third page will be all chapter 3. And the fourth page will be all chapter 4. Any questions? Okay. Uh, yeah. General idea is I posted last semester's exam, as I said. What's going to happen is today we start chapter 4. Wednesday we finish chapter 4. Monday of next week, I'll go over last semester's exam. And when I go over last semester's exam, I'll post the solutions. They're not posted yet, but they will be posted. And as I said, I've already posted up the exam in this format. If you just want to see the exam in general and don't want to care about the format being the same, I have, I have also posted it in PDF form, where the PDF is what it would have looked like if we were in person, but has just, it's the exact same thing. Just less pictures on it because of space. If you have issues with those times or anything, let me know, send me an email or talk to me. We can work it out. Okay. So let's talk the actual chapter 4 then, if there's no questions. And we're going to start by talking about work. Mechanical work, which uses the symbol capital W. Your lowercase w is weight, capital W is work. What it is any time you do a constant force to an object, work is the component of the force along the direction of displacement times the displacement, which was a lot of words, but here's the general idea. If I pull this block with a constant force, work is just going to be how much force did I pull it by? What is the force? Times how far did it move? If it moves from there to there, which I think is how far it went, from there to there, I would just say the work is how much force I used times how far I pulled it. Work does not tell you how long it took. Work does not tell you the velocity or the acceleration of the object, although you can get velocity from it, and we'll talk about that in a little bit. Work is just how hard did you push or pull this thing, and how far did you do it, where it is a scalar quantity. Putting this mathematical terms, assuming that the force and displacement are parallel, work is force times displacement. If force and displacement are not parallel, well, we'll come back to that. So, yeah, there's the equation. Work is FD. Work does have its own units. If I was to work out in units, it would be force, which is in newtons, times displacement, which is in meters, which are a Newton meter. But a Newton meter is used commonly enough, it gets its own unit called a joule, which is a capital J. And anytime we talk about work, we will use joules. Of note, interesting thing, torque is also measured in Newton meters, but we never say torque is in joules. Joules is just used to explain energy and work. The American unit is the foot pound. That's just what it is. There's no better term. Joules is more commonly used than foot pounds. Now, this equation does assume the force and displacement are parallel. That I'm pulling to the right, left, so it goes to the left. If there's an angle between them like this, in this case, when I pull here, the displacement is still directly to the left, but I was pulling this up at this angle, which means there was a angle between them, some angle theta between this force and displacement. If that is the case, like this, the equation for work does shift a little bit, and that is the full equation for work. The work is actually force times displacement times the cosine of the angle between them. If I don't give you an angle, assume they're parallel, or basically assume the angle is 0 degrees because the cosine of 0 is 1. But if I give an angle, it's actually force times displacement cosine of the angle between them. Make sure your calculator is in degrees. Okay. So let's say you push on a thing. You push on a thing, you're applying a force. If you're applying a force, you're doing work, assuming it's moving. Of note though, that if I go and push on something heavy and get it moving, Newton's third law says if I push a block, the block pushes me. And so if you push something heavy, you'll feel the force acting on you. For that reason, people often talk about work as work done against something. That if you slide something and you make it move, you'll say the work done against friction. Or if you lift something up, you'll say the work done against gravity. That's just a common way to say it. See, the reason if you lift something, the reason it takes effort to lift something, that if we're lifting weights like this, it takes some effort, is because you're trying to overcome gravity. If you lift a weight, you need to apply a force to counteract gravity, assuming you're lifting at a constant velocity. If you're doing it fast, you got to go fast, you got to apply more force than that. And so to lift something, you need to overcome gravity. Well, gravity is mg. And therefore, the minimum work required to lift anything, the work would be the force times the distance you lift it. The work required to lift something up will always be mgd. It's mass times gravity times the distance you lift it, or its weight times the distance you lift it. And that's how much work one applies to lift something up. Okay. Here's the crazy thing about work. Work is a scalar. And I've said before in chapter 2 that scalars are almost always positive. I said how speed could never be a negative number. Work is a special type of scalar. Work can be negative. And here's the idea. Work is positive anytime you're doing something that it doesn't naturally want to do. Like, oops, fling that on the ground. Okay. Like if I lift this up. If I lift this ball up, I'm doing work to it. Thing is, this ball on its own wants to fall. That's what it wants to do. If I, instead of dropping this ball, but take it and place it in my hand, that is actually negative work. Anytime you lower something, it takes work just negative, because it's harder to show with this than it is with. Okay. So I have this weight on a string, right? Right now, I'm applying a force upwards because the string is applying a force. That doesn't show up that well. I'll just use my short as a background. I'm applying a force up to hold this up. And if I lift it up, the displacement is up, but the force is still up. If I lower this down, I'm still applying a force up, a smaller one, but I'm still applying a force up because I'm still pulling up with the string. If I was applying a force down, I'd have to be like this and yanking it downwards. And so even if I take this and lower it down, I'm applying a force upwards while its displacement is downwards. That means there's a 180 angle degree between force and displacement. That means work is negative. Work will be negative anytime you are keeping something from doing what it naturally wants to do. You see, if I lower this weight, it naturally just wants to fall. And as it plummets downwards, it'll go down at a rate g. By setting it down, by instead of letting it fall, but just by taking it and slowly putting it down, I'm decreasing the rate of it doing what it wants to do. And since I'm decreasing the rate of doing what it wants to actually do, that is negative work. Negative work is when you make something go slower than it wants to. Okay? Now, the reason we care about work is because we don't really care about work. We want to get into what work would turn into. And this would be the idea of the work energy theorem. You see, anytime you do work to something, you are changing its energy. And this is kind of the most circular definition of arguments I'm going to give. Energy is known as the ability to do work. And I defined energy as initially that you do work, you change energy, and the definition of energy is the ability to do work. It's kind of circular. But here's the idea. Energy is the ability to make changes to something, to change its velocity, to change its temperature, to change its position. Energy is a intrinsic combination of stuff that allows anything to do anything. That energy is the general idea of how things react and move and change temperature and light up and glow and explode and all of that. Now, there are many forms of energy, and I'm going to talk about all of them in more detail at the end or during class Wednesday. But general idea, there is chemical energy. This is the energy made up from the chemistry and made up of the molecules. This is why when you eat something, you get energy. It's because when you eat something, you're breaking apart molecules and using it. There's nuclear energy, the energy stored in the nucleus. There's electric magnetic energy. You plug something in, it does stuff. That's what that is. There's mechanical energy, the energy of movement, and thermal energy, the energy of heat. But in all cases, total energy is conserved. And any time you do work on something, you are changing the energy, possibly from one type to another, maybe making thermal energy mechanical energy or vice versa, or maybe just shifting within that type. Today, we are only going to talk about mechanical energy. We're going to cover a bunch more of these energies later on in the semester. In fact, we will touch on all of these but nuclear energies. That we don't talk about. And mechanical energy is the energy of movement. And mechanical energy is just the energy of something, yeah, physically moving. It is the energy due to placement, aka where is a thing, and if it's moving. That's what mechanical energy is. Now, mechanical energy has two different forms, kinetic energy and potential energy. Actually, to be fair, most of these do. Thermal energy is kinetic and potential, electronic energy has kinetic and potential. They just have different names. But mechanical energy has kinetic energy and potential energy. Kinetic energy is the energy of something actually moving, and potential energy is something waiting to become energy and is the energy of position. Any questions though? So let's do a derivation. Let's say a constant net force does work on an object. Work is applied. If work is applied, we're applying a force that's going to change the velocity. Well, work is force times displacement. But we know force is ma. So work should be ma times displacement. Now, from way back when in chapter 2, we said that if you drop something, the distance it falls is 1/2 at squared. I'm going to take that d and I'm going to plug it in at the end of my mat equation. Factor through my a's. I'm going to factor back out my at's. But we know velocity is a times t. And I get this equation here. Now that isn't actually an equation for work. Work is force times displacement. But if I say that by doing a work, I cause a mass times acceleration. If by doing a work, I cause this mass times acceleration, that my work becomes a 1/2 mv squared. And what that really is that is the equation for kinetic energy. Anytime you have something moving, it'll have a certain amount of kinetic energy measured in joules. Kinetic energy is 1/2 mv squared. 1/2 the mass times the velocity squared. And if I take a coat and have it go sliding down, when this guy's moving, anytime it's moving, as this goes down here, it's speeding up, going faster and faster and faster. At all points, that means it's just gaining kinetic energy. It's gaining kinetic energy because its velocity goes up. The faster something's moving, the more kinetic energy. The heavier something is, the more kinetic energy. Okay. Is that a question or? Okay, I'm going to assume it's not a question because you're not actually saying anything. But if it is, feel free to interrupt and ask. Now, let's say we got a pitcher throwing a baseball, right? So you take a ball, you wind up, you throw. I can't move my shoulder like that because of an injury. When a pitcher throws a ball, they are bringing the ball from rest, not moving, to some velocity. It's then flying out of their hands. That means they're changing the kinetic energy. To change the kinetic energy of something, you must do work on it. This is called the work kinetic energy theorem. That the reason a pitcher can take a ball that isn't moving and turn it into one that is moving very, very fast is because you're doing work. Anytime you do work on an object, you can change the kinetic energy. That is the idea of the work kinetic energy theorem. Now, I kind of said something that was a little bit of a stretch of the truth, so I do want to make sure that I get this across. I said before that work and energy, the direct relationship. When you talk about work, you normally only talk about mechanical energy. If you are changing the thermal energy of something, that has its own phrase. If you're changing the chemical energy of something, that has its own word too. But anytime you do work, you are changing the kinetic energy. And when you change the kinetic energy, that means, yeah, it probably speeds up. And that's the equation just says work is change in kinetic energy. that work is kinetic energy final minus kinetic energy initial, where kinetic energy is 1/2 mv squared. And so when work is done by a net force on an object, and it only changes the object's speed. Keep in mind, you might also be changing the temperature. You might also be changing the temperature. You might also making it glow somehow. That you rub two things together and like you rub two sticks together and they catch fire. There's something else going there. But if you do work by something and the only thing that changes is its speed, work equals the change in kinetic energy. Now, if you're changing things other than the speed, I'll come back to that in a second. But when you do work, you change the kinetic energy. 1/2 mv final squared minus 1/2 mv initial squared, that will be work. Here's a practical use of this. Let's say you're driving at a speed v. You slam on the brakes, coming to rest. When you slam on the brakes, what's happening is friction is doing work on your car. And by slamming on the brakes, you're applying a force. That force is going to slow you down. Now, if you're going and driving pretty fast and slam on the brakes and go until you're stopped, if you're going until you're stopped, that means your final velocity is 0 because you stopped. And so if you're driving and slam on the brakes, the work you do will be negative KE, or the negative 1/2 mv initial squared. Now keep in mind, work is force times displacement, which means force times displacement is 1/2 mv squared. This actually says if you slam on the brakes, the faster you're going, the farther you'll slide to stop. And it actually shows us squared. That if you double your speed, you'll skid 4 times as far when you slam on the brakes. If you triple your speed, you'll go 9 times further in your slide. This is why if you're going real fast and slam on the brakes, you skid a long time. It's because of this idea of work and displacement. Okay? Okay, I'm gonna do an example. This example, when we were in class, always involved me using my bag and just dragging it across desks. But I'm not gonna bother dragging my bag across desks because you're not here anyways. So we're gonna use a block instead. And let's say I pull. This is a 2 kilogram laptop bag, here represented by this wooden block. Let's say I pull this block using 25 joules of work to pull a 2 kilogram block. And say if it starts from rest when I use this 25 joules of work, what's the final velocity? Well, work is changed in kinetic energy. And so work is 1/2 mv final squared minus 1/2 mv initial squared. Now, if it started at rest means it initially had no velocity. So my initial is 0. And so the work is just 1/2 mv squared. If I want to find the velocity when I pull this thing, I'll simply multiply both sides by 2, divide both sides by m, and square root. And I can plug in my numbers and get an answer. And say if I pull this thing from rest, it'll then be going at 5 meters per second using that much work. Okay. Now there's a real issue there though. Let's go back to this video. I'll just make it smaller so I don't have to cover things. This guy's going at a pretty constant velocity. And I'm doing work. I'm pulling a force. I'm moving at a distance. So it should be speeding up. The work kinetic energy theorem says if I do work, it gets an increase in velocity. And you can see this isn't increase in velocity. It's sliding. I'm doing work, but it's going the same speed. That's because there's something else going on here. And that is friction. The work kinetic energy theorem assumes all of the work goes to changing the speed. If you have any of the work going elsewhere, it doesn't necessarily immediately work. You see the friction. If when I take that block and slide it across the desk, there is friction. Anytime you have friction, friction is a non-conservative force. And what happens? Okay, if you take your hands and rub them together, they heat up, right? They heat up because of friction. And if I take that block and slide it across the desk, it's going to heat up. It's going to heat up because of friction. And you see, work is the change in kinetic energy. But what we talked about so far was only mechanical kinetic energy. There is also thermal kinetic energy. And here's the general idea. What we view as temperature is a way to relate the movement of molecules. Something that is cold has very slow moving molecules in it. And something that's hot has really fast moving molecules in it. Anytime you do work, there is a change in kinetic energy. But sometimes the thing itself is not its kinetic energy that changes, it is the molecules inside. When I slide this block across the table, its velocity might not be going up, but the molecules of the wooden block touching the desk, they're moving a little faster inside. Now, the speed of molecules inside is called the internal energy and is related to temperature. And so if you have friction, work is still changing kinetic energy. It's just some of that kinetic energy is thermal kinetic energy. For the most part, we're only going to talk about conservative forces, aka when work equals change in mechanical kinetic energy. Because when you deal with thermal kinetic energy, that becomes a whole nother bit of complication. Although it's a simple equation. It's 3/2 k sub b times t. And so when you do work, if you have friction, it doesn't all become mechanical energy. Some becomes thermal energy. But if we have no friction, then all of the work becomes mechanical kinetic energy. Make sense? Okay, let's talk about something else. I got this cart. I let go, and it goes sliding down to the bottom there, right? Just whoop. We're going to talk about to that point. When I let go of this cart and let it fall to there, what's happening? Here, I can let it continue up. What's happening when I let this go and it goes down is that gravity, I'll just do this, guy, so you don't have to worry about the backup yet. What happens is gravity is pulling this coat down. When gravity pulls this coat down, it's doing work. It's pulling it downwards. Because it's pulling it downward, it's letting the coal move. But what I can say is that doing this work, I'm getting it kinetic energy. But that kinetic energy only happened because I held this up at the top of a hill. Going back to the red call, it only gains speed because right now it's at the top of a hill and gravity is going to bring it down, turning that into kinetic energy. And this brings us to potential energy. Potential energy is the energy stored in an object. That when I bring a ball to the top of the hill, I'm giving it potential energy. And potential energy is energy that isn't doing anything. It's energy that is ready to do something. It wants to do something. It's not doing anything now, but it will do something once you let it go. A spring is a type of potential energy. I have this thing with elastic arms that launches. Right, if I pull this down, I'm getting it ready to do something. By pulling this down, I'm prepping it and getting it set so that when I let go, it fires. That is a type of potential energy. That potential energy is the potential to do energy. And it is something that can turn into kinetic or other forms of energy. And it is energy due to location. It's the energy of something waiting to be set free. Now, we're only going to talk about one type of potential energy in this class, and that is gravitational potential energy. Anytime you lift something off the ground and you lift something a height h, you give it potential energy. And gravitational potential energy, and just PE is potential energy. I don't think I said out loud KE is kinetic energy, but gravitational potential energy is just the weight of something times the height you lift it, mgh. That if I take this tape measure and lift it up a height, I am giving it potential energy. Potential energy that can turn into it falling. If I take this coat and brought it from the bottom, oops, that went too fast. If I take this coat from the bottom and start pulling it back up the ramp, what I'm doing is I'm giving it potential energy. I'm giving it potential energy because I'm lifting it up. I'm moving it to a higher spot. Now note, if I just do this and move side to side without changing the height, that's no change in potential energy. The fact that the coat moved in from here to there, as in, sorry, from here to there, like it moved that far horizontally, that's nothing for potential energy. The only thing that matters is that it went from this height to this height, and that would be the increase in potential energy. Potential energy, once again, is just mgh. Now, the whole how do you measure h is kind of weird, though, because let's say, can I get that on the camera? Nope. Let's say I got this book and it's over a table, and I say I want to measure its potential energy. I'd probably just say the potential energy is the distance from here to here. Let's switch the colors of that. But if I then move this book and take a step to the right, and now it's over the ground, without changing the height, I change the distance to the ground. And if I take it out a window, I change the height of the ground again. Since height and length is relative, the question is, what do you measure height from? General idea. In any given problem, you define where h equals 0. H can be 0 wherever the hell you want, as long as you're consistent. If you define that this table is your height equals 0, that's fine, as long as you always define that table as your height equals 0. That being said, potential energy can be negative, because if I define this height as 0 and the book ends up down here underneath the table, if you're beneath your 0 point, that is negative potential energy. I recommend always labeling your lowest point as 0. If your lowest point is 0, you never have to worry about being negative. It makes life easier. Now, in general, if you have no friction, and we're going to kind of assume no friction moving forward for the most part, although in like 3 slides I talk about friction again. If you have no friction, something will have some potential energy. Now look at these. I got these 2 ramps and these 2 balls on the ramp. Both of these balls have the exact same potential energy. They have the exact same potential energy because they're at the same height. And yes, they're at the top of different shaped ramps, but that doesn't matter. Potential energy is just height off the ground. And anytime you do work on something, you can say that you change the kinetic energy, but you can also, when you do work, change the potential energy. Work can do one of 2 things. If I lift something, I'm not necessarily giving it more kinetic energy, but when I lift it, I give it potential energy. Work is always change in kinetic energy or negative change in potential energy. That if you do work, you can make something go higher. You can lift it up. And so the process of me taking this call, and moving it from here and sliding it up the ramp like so, that would take work. The work based off the potential energy. Now, the law of conservation of energy says energy cannot be created or destroyed. Total energy in a system is always constant. And so however much energy you have initially equals however much energy you have on the end. And in any system, no matter what, energy is always conserved. You can never create or destroy energy. It can change types, though. You can take energy and turn kinetic energy into thermal energy, or you can change mechanical energy into electrical energy. That's what a generator is. Well, it depends on the type of generator. Sometimes it's changing chemical into electrical. She loves that light. But energy is never created or destroyed. Conservation of mechanical energy only happens when the energy doesn't change form. Conservation of mechanical energy means there is no heat or change in temperature. It only happens when there's no friction. This car that this person seemingly is trashing for no reason has sparks coming off it. Sparks coming off it means some of the energy is going to heat. that cannot use conservation mechanical energy. But if you have no friction, mechanical energy will be conserved. And so that anytime you have no friction, the total mechanical energy, which will be the kinetic energy plus potential energy, will be the same before and after in the system. That if you have no friction, initial total energy equals final total energy, where E is energy, which means kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Or 1/2 mv final initial plus, 1/2 mv initial squared plus mgh initial equals 1/2 mv final squared plus mgh final. That's the general idea. Anytime you have conservation of mechanical energy, anytime there's no friction, the total energy will be the same, initial and final. Now here's the interesting thing. Both of these balls start at the same height. That means both of these balls have the same potential energy. When they slide down that ramp at the bottom, they both have the same height again. That means both of those balls have the exact same velocity at the bottom. Likewise, I have showing these cars. If I set both cars going, like so, both of these cars started at the exact same height. They both started here. Both of these cars ended at the exact same height. That means at the end, they had the exact same velocity. At all different spots, they'll have different velocities, and they took different times to get there. But conservation of energy says as long as there's no friction, and this thing is nearly frictionless, that as long as there's no friction, they have the exact same velocity at any given height. Because the energy is the same. That this is, as I said, this is nearly frictionless. At all points on this ramp, the energy is the total. Now, if I look at just my red car, right now it has a certain amount of energy. The energy is its height off the table times, and the energy from potential, the height off the table, and the kinetic energy from velocity. Right now it's not moving, so it's just potential energy. When this starts to go down, it is dropping in height. As it drops in height, its potential energy goes down. That means its kinetic energy will go up to counteract, and it goes faster and faster and faster as it gets kinetic energy until it hits the lowest point. At this lowest point, it has basically no potential energy. It's all the way at the bottom. And it's going real fast. But the total energy is still the same. The total energy is still the same because it's going to be conserved. On its way back up, its potential energy is now decreasing. As its potential energy decreases, because it goes up, sorry, I said that. Let me try that again. As it goes up, its potential energy is increasing. I think I said that wrong. As its potential energy increases because it's going up, that means its kinetic energy must decrease. Its kinetic energy decreases because the total energy is the same. And as the kinetic energy decreases, it goes slower until it gets to the top. As something moves up and down, the total energy is always the same. And just as it goes down, the potential energy decreases, kinetic energy increases. And as it goes up, the potential energy increases, kinetic energy decreases. But at all points, the total energy is the same. That the total energy, kinetic plus potential, is the same. And as long as you have no friction, the net work will be zero. That all of the energy will just shift between kinetic and potential. And will change velocity as a function of height, but we'll just go through and always have the same total energy. Any questions though? Okay, let's go back to my racetrack. So here is the version with both cars. What I did is I measured the height. Oh, that's not both cars. That's both cars. What I did is I measured the height right here. Right now, both of these coats from the table, and I know it's like kind of off the table the way I did this, but I did it when it was fully on a table the first time. Right now, both these coats have a height of 0.595 meters above the table. Then they go all the way through. And right when they pass through that photo gate, They have a height of 0.475 meters off the table. And what I'll say is they both start with no initial velocity. I just hold them there and let go. So the initial velocity is 0. And what I can say is all points they have the same energy. But more importantly, when they hit that photo gate, when they hit the end, I should know their velocity. Because I can say that at all points energy is conserved. That the kinetic plus potential initial equals their kinetic plus potential final. Now they started at rest. V initial was 0. And since V initial was 0, this term right here would disappear because it's 0. And if I look at this, every single term has an m in it. There's an m every step of the way. And so if I divide everything by m, my m's cancel out. If I subtract GH final from both sides, and then multiply both sides by 2, I can say that V final is 2 times GH initial minus GH final. And by square rooting, I can actually get what the velocity should be when they hit that photo gate. Now, if we were doing this in person, I would have that photo gate on and be timing it. And I can read the velocity of both of these coats right when they pass through right there and there as they pass through the photo gate. And I can tell you from experience, they're normally about 1.3 meters per second and a little off from each other because there is some friction. This assumes 0 friction, and there is a little bit, but there isn't much. And it doesn't matter that one goes down and up and the other one just steadily moves forward. That makes no difference. The velocity at that height is the same, following conservation of energy. Questions though? Let's do an example problem with the time I have left. An Olympic ski jump has a height of 120 meters. Assuming no friction, how fast is a jumper going when they leave the end of the ramp? Now, I think this is a batshit crazy thing to be going at speeds we're going to talk about in a second in nothing but spandex and big pointy things attached to your feet. But let's go through. In an Olympic ski jump, they normally push off to give them some initial velocity. Let's ignore that fact. Let's just say the ski jumper is just going to take and just step on the top of the ramp with no initial velocity and figure out how fast do they go off the ramp. What I can do is I got to find my 0. And I'm going to say they start a height h up. And I'm going to define the bottom of my ramp as potential energy is 0. I'm going to say, oops, I want this, that this right here, this is my 0 point, which means up here, my height is h, or 120 meters. What I'll do is I'll find an equation for the energy at all points. See, I'll just say energy at the top. Energy at the top is kinetic plus potential. At the top, I said they had no kinetic. So my energy at the top is just potential energy. The energy at the top is mgh. At the bottom, the energy is kinetic plus potential. But they're at the bottom. Their height is 0. So my energy at the bottom is just 1/2 mv squared. And I'll use conservation of energy to say the energy at the top equals the energy at the bottom. And so therefore, mgh equals 1/2 mv squared. I can divide both sides by m. At this point, I'm going to make some space. I can multiply both sides by 2, and I can square root. And by plugging in values, I can solve for how fast. And it says a ski jumper should be going at 48.5 meters per second at the bottom of the ramp. Now, for the record, that is 108 miles per hour, which is crazy. And it's not the actual real number. Normally, people are going about 70 miles per hour and they go off the ramp. This change is because of air resistance and friction. There is friction, there is air resistance. But I would like to propose that going 70 miles per hour in nothing but spandex with big pointy things attached to your feet is still crazy. But if it was completely frictionless, you'd be going at 108. With friction, you go about 70. Now, there is one issue with conservation of energy. I say this person leaves the ramp at 48.5 meters per second. But that's not a complete velocity. As we covered in chapter 2, velocity is a vector. That when you say the velocity, you don't just say the magnitude, you have to say the direction. This doesn't tell me what direction the person is moving. Anytime you use conservation of energy, you will not get the direction. If you want to get the direction, you're just going to need to look at the direction. You're going to have to say, hey, this person goes off the ramp going that way. That's the direction. The direction will be found just by looking at the situation. Any questions though? Now note, I said this person should be going at 108 miles per hour. In real life, they're going 70. That doesn't mean energy isn't conserved. Energy is always conserved. It's just sometimes the energy switches form. If I tell you to ignore friction, then you can use conservation of mechanical energy. If you have friction, and then it is that total energy conserved, but something goes to somewhere else. If I pick up something and throw it, the energy is coming from inside me. I ate something. Actually, I haven't eaten anything yet today. I ate something yesterday. That gave me energy. That's energy I use for movement. That's turning chemical energy inside me to movement. Going back to the pitcher, a pitcher throws a ball, that energy that becomes kinetic is becoming from the energy inside. Total energy is always conserved. And in any system, the total energy is always the same before and after. But if we have no friction, we can say mechanical energy is conserved. And if mechanical energy is conserved, initial energy equals final energy. That kinetic plus potential initial equals kinetic plus potential final. Any questions though? Okay. That brings me to a completely different topic. And so I am going to pause there because I only have 3 minutes left, and we will talk about the next thing, which is power. We'll talk about power on Wednesday. But other than that, have a good day. There we go.